Hello again, friends. In this video, we're going to be trying to find the area between curves using integration, and we're going to be trying to do this in terms of y. So, to get us started, what we've done in the past when we try to figure out the area between curves, or between like a curve and an axis, what we've done is we've mainly used approximation techniques. So, for example, if we were to draw this out again, these two functions that we have here, we have x equals the square root of y, and we have x equals y. So here's x equals y, and here's kind of what x equals the square root of y is, and this is 1 and 1. So now that I've drawn this a little bit bigger, what we've done is we've used, like I said, approximation techniques. So what we've done is we've divided this up into like equal parts. So here I have it divided up into fourths, and we've drawn like rectangles. So we drew, let's switch my colors so you can see this better. We've taken from our equal parts, we've drawn a rectangle up to a certain point on our function, either from the left, the right, or from the midpoint. So here's another rectangle. Right? But now we see we have two rectangles, correct? So we're going to have to do this for both, or not two rectangles, excuse me, two functions. We have to do this for both functions. So starting from here, we're going to come up to reaches our x equals y function. We have another one. And we see that both these functions meet at the same point, so they're going to have the same rectangle. So when we try to figure out what the area of the banana peel shape is, when we try to approximate it, we're going to try to figure out what the area is of these rectangles right here. So in order to do that, like I said, we have our equal widths of our rectangles, and now we have to multiply it by the length of our rectangles, which we see is going to be defined by what our pink function is, the length of this rectangle minus the length of the blue rectangle. That'll just get us the length of this little piece right here. So like I said, we take the length of the pink rectangle up to our I go from here, sorry, length of our pink rectangle up to our point right here, up to our function x equals the square root of y at this point for y, and we're going to subtract out the length of the blue rectangle up to this point on the function x equals y. So at the same point y, we're going to subtract the pink length minus our blue length at the same point, and that's going to get us our length. And we see we're going to have the same thing when we use integration. We're going to do a same, kind of a similar method to figure out what our area is. So with integration, what we have to do, once again, we have to pick a rectangle. And so here I'm going to go up to my function, well, x equals the square root of y, and this has an infinitely small width, dy, right? And it goes all the way up to here. Now, what I said before we had to do is we had to subtract out, in order to get just the banana peel width, we have to subtract out the width up to the point on the function x equals y. So we're going to take the entire length up to x equals the square root of y, and subtract out the length from x equals y. So all we're left with is just the width inside of there. So that's how, for our format, for our integral, That's what we get. We have the integral from some bounds a to b in terms of y. We're going to take the function that's furthest to the right and subtract out the function that's furthest to the left, because the function, right, is what's going to, the function defines where our length goes to for both pieces, right? The entire function does. And then we're going to multiply it by our width dy. So rewriting this, you see we have the integral from our bounds from 0 to 1. Our function on the right is the square root of y. We're going to subtract out then our function on the left, which is x, because our two functions determine the lengths of the rectangles, and then dy. Now if I were to rewrite this, it's the same thing as y to the 1/2 minus, oops, this is supposed to be a y, right, because we are working in terms of y. So minus y dy. When we integrate, we add 1 to our exponent, so we get 3/2. Multiply by reciprocal. Once again, add 1 to our exponent. Multiply by reciprocal. Don't forget your sign. And now we have to evaluate with our bounds. So when we plug in 1, we get 2/3 times 1 to the 3/2 minus 1/2 times 1 squared. When we plug in 0, we're just going to get 0. So all we're left with is 2/3 minus 1/2, which is the same thing as 4/6 minus 3/6. So all we're left with is a grand total of 1/6 for our area of this banana peel shape between these two curves when we take our area using integration in terms of y.